operate machines for mining and refining water on the moon and Mars to produce rocket propellant. Last December, their company's robot was named as first among 6 finalists competing for NASA's $1.5 million Break the Ice Lunar Challenge. And he's going to talk about in situ resource utilization. So it's your floor, Mihir.
Yeah, thank you so much for that introduction, Dr. Rhodes. Can I get a quick comm check?
Oh, yeah, we can hear you. Yep.
Awesome. Okay, let me share my screen. Great. Can everyone see my slides?
Yep.
Awesome. All right. So let's dive right into things here. There we go. So today we're going to be talking about enabling life in space, how exactly we can do that, and how in situ resource utilization plays a role in enabling life in space. We'll be diving into what exactly is living in space and what exactly I define that as, some of the technical challenges there, and some of the current state of the art, as well as some of the stuff that we're working on here at Starpath Robotics, and how we believe that producing water and rocket propellant on the surface of the moon is the next step in, pushing humanity into outer space. Great. So a quick definition of what I think life in space exactly is. I define it as a sustained presence of a cislunar economy, as well as a sustained presence of life beyond geotechnical orbit. A cislunar economy refers to economic activities or infrastructure or development initiatives that can take place in the region of space between the Earth and the Moon, which is commonly known as cislunar space. Typical activities include satellite deployment, space tourism, or space manufacturing. Some important next steps to enable a cislunar economy, I believe, is first creating fully reusable rockets, and we'll explain why I believe that's a critical step. And the next is the idea of in situ resource utilization, which is using the resources that are available to us in space rather than using the resources here on Earth and needing to bring those resources to, say, the surface of the moon or Mars in order to carry out the successful completion of that mission. And specifically, we'll be diving into the 3, what I call sub-core components of things that will be in space. This includes vehicles or rockets, deep space technology, and life, humanity, and their presence there. Great, so here are some of the challenges associated with creating, launch vehicles. Currently, rockets have to be thrown away after being used. And this makes the cost of launch extremely high, because you have to factor in the cost of the rocket, the cost of the fuel, plus some amount for profit. This cost drives this cost to launch, or cost per kilogram to a certain orbit, say low Earth orbit, drives the cost too high to the point where it is impossible to structure a business case around cislunar activity. Your overhead is just too great. This is the main challenge that rockets currently present to small businesses and companies that are looking to create life in space. Some of the current challenges that deep space technology faces, a lot of the machines that we have, spent a lot of time engineering are developed to handle the environment of Earth rather than the environments that you find in space. Earth is a much friendlier environment than whatever you will find, on the moon or Europa, or, if you're a satellite in orbit and in vacuum. Your technology can experience large temperature fluctuations. You're exposed to radiation, which can tend to flip bits and computing hardware and so on. You have to be able to handle a hard vacuum. And in the case of the moon, specifically as a next step, the lunar environment is very dusty. There's no atmosphere, there's no erosion, so all of the dust particles are like tiny little knives that get everywhere and tear through mechanisms. These are some of the standard challenges that you face when you develop deep space technology. And finally, there's a whole host of health risks that are present for humans should they want to go into space. Your body is used to fighting the force of gravity when it operates. Your heart is pumping blood to your head against gravity, and that's not really the case when you're in microgravity. And so this often can lead to a rush of blood to the head, which can lead to vision problems, can have all sorts of cardiovascular health issues, you can have brain problems. The lack of having to fight the force of gravity with your legs and your muscles can lead to muscular atrophy and bone degradation. And the other biggest thing is that humans require consumables. You know, we need food, we need water, we need oxygen in order to live. And none of these are, you know, readily available to us in space. So some of the current state of the art of vehicles that we have today, specifically, you know, I'm obviously a little bit of a fan of SpaceX here, but currently the Falcon 9 and Falcon Heavy are the best in terms of cost of launch. Falcon 9 sits at about $2,700 per kilo, while Falcon Heavy is at around $1,500 per kilo. Typically, companies will use Falcon 9 if they can't fill out the full payload capacity of Falcon Heavy, which is often usually the case. So most companies have to pay the $2,700 price. One thing to note here with this state of the art is that both of these rockets are partially reusable. Their second stage or the upper stage can land, and you've probably seen videos of it landing on on a boat out in the sea and so on. They are not fully reusable. The booster is thrown away in both situations. And some of the state of the art for deep space technology. Now, this sort of space technology is very different than what we're developing at Starpath Robotics. What usually happens is, since you can't structure a business case around, or a commercial business case around deep space tech, typically the only projects that get funded are ones that are funded by a government and are usually tools of scientific discovery. They're not, for example, machines that are manufactured in high volume and manufactured to do a specific task. They're kind of a jack of all trades. They may have, you know, a large sensor suite and so on associated with them. They do not carry specific tools to carry out tasks such as mining or refining or hydrolysis and so on. However, there are, you know, a large number of deep space technology that is present in robotic devices that are present on the moon and Mars. The Mars helicopter is one. Rest in peace, Ingenuity did a great job. But that is typically the state of the art, and there's not that much commercial technology out there. And finally, here's some of the state of the art as far as humanity. Typically, we just have astronauts and rich people going to space, with rich people basically paying for space tours or space tourism on rockets that are either suborbital in the case of Blue Origin, or at most will fly to, say, like low Earth orbit. Typically, astronauts, you know, do not go beyond the orbits of the Earth. Typically, they'll go to the International Space Station and so on. They do not go to the lunar surface. The last astronaut to go to the lunar surface was Gene Cernan back in 1972. And we have not really been sending people into deep space since then. Oftentimes, this is because of the, you know, perceived risk to their life and to their health as well. So some of the potential solutions for this high cost to launch for vehicles is to make rockets that are fully reusable. Starship is an example of this. With the idea being that Starship reduces costs even from its predecessor Falcon 9 by an order of magnitude, down from $2,700 down to $90 per kilo. This actually makes it possible to structure a business case around extraterrestrial operations. The low cost of launch of $90 per kilo is, something that could really enable a lot of businesses moving forward. However, Starship is still in development and has not yet completed a successful test flight. Last time, it unfortunately failed during stage separation between its booster and its and ship, the second stage. With the presence of Starship, though, however, there have been a lot of small businesses that are currently popping up and are undertaking R&D efforts to make technology that can exist on the surface of the moon. In the picture here, we have the Flex rover created by Astrolab Venturi. They're structuring a business around lunar operations, basically acting as like a car in space for astronauts during the Artemis missions. They're also capable of payload manipulation on the surface of the moon and are essentially charging companies for transportation services on the moon. These companies are still more in the R&D phase and have mainly kind of timed their creation based on Starship and the emergence of reusable rockets. So I would claim that Starpath falls under this category of technology that is up and coming. Great, so let's take a deeper look into in-situ resource utilization. As I mentioned before, in-situ resource utilization is the process of using resources that you find in space rather than bringing those resources from Earth. It is considered essential for creating a sustained presence, human presence on the moon, and for enabling future missions, because you don't have the overhead of having to have resupply missions in order to facilitate the establishment of a lunar base or colonies and so on. Every time thousands of people on the surface of the moon needed to drink water and we had to fly that from Earth to the moon, that would make living on the moon pretty impossible. So this is even more the case for Mars. The moon is much, much closer to us. Mars is much farther, and distances in space are much greater than objects in space. We actually cannot fly to Mars and back on a single Starship tank, Starship being the current largest rocket in development. You'd essentially have to waste 10 Starships to bring enough fuel for that other Starship to come back, which means that people that are going to Mars are basically buying either a one-way ticket or have to buy an extremely, extremely expensive, round trip. If we want to go past the moon and past Mars, it's essential that we start using the resources that we have available to us out there. If rockets are meant to be more like cars or airplanes in the sense that they're reusable, you don't throw them away after a single use, well, cars and airplanes wouldn't be going anywhere if there was only one gas station for each on Earth. So that brings us to Starpath Robotics, which is a small business me and a few of my friends from SpaceX decided to start back in 2022. We create hardware to produce rocket propellant on the surface of the moon and on the surface of Mars. Specifically focusing on the moon for now, as the moon is more of a challenging environment to handle as opposed to Mars, and the moon is much, much closer, as well as a lot more funding options for developing lunar tech. Here's just a quick overview of what we do, just reiterating that rocket propellant, which is what we're trying to produce, is usually some form of liquid oxygen combusting with either hydrogen or hydrocarbon. This is usually the case for liquid propellant engines. And the biggest chunk of the fuel is usually liquid oxygen. For Starship, it's about 78% ox, while Blue Moon is about 85% ox. Our end goal, and this is something that we all really buy into and believe in, is establishing a lunar and a Martian base. and enabling life in space. I'm not going to talk about, my personal philosophy on why I think this is a necessity for humanity, but this is a mission that we all really buy into and that we're trying to, push the pen forward at this. Our business model is to have a company or a vehicle manufacturer, such as SpaceX, such as Blue Origin, fly us to the surface of the moon, deploy our tech, produce the rocket propellant, and then have that same rocket refuel using our produced rocket propellant. In the sense, they don't need to carry enough fuel to get there and back. They just have to carry enough fuel to get us there. Here's a quick overview of the ConOps of how exactly that'll happen. The reason why we chose this business case as our, to structure our whole business and as our business model is because this really enables all other forms of, lunar activity and lunar businesses, space tourism, mining, space manufacturing, in-space satellite refueling. The cost of all of these gets driven down by a lot if you're able to create liquid oxygen on the moon. Throughout our process, I know I talk a lot about liquid oxygen and water as being what we produce, but there are other, important aspects of lunar regolith and products which we can also sell. Those products mainly being things such as helium-3, which is considered very valuable on Earth, silicon, which is found in large quantities in the lunar regolith or the lunar dirt. Water is another great example, and hydrogen. And in the case of Mars, you can actually create methane using the Sabatier process. I can talk a little bit about the Sabatier process later. So for Starpath, we have a 2-mission plan currently. Our first mission is a demo mission where we deploy our technology stack and we produce rocket propellant at a scale of about 1 Starship tank per year. This is mainly meant to de-risk our technology and establish confidence in the ability to create rocket propellant on the moon at scale. When I say at scale, I mean we're doing much, much more than producing, say a few grams of oxygen here and there. We're trying to continually produce enough oxygen to refuel a full Starship. Our second mission, should that mission be successful, is our full-scale version of our technology, which would be able to refuel about 10 Starships every year. By refueling on the surface of the moon, Starship is essentially saving itself about $150 million worth of, rocket propellant and of R&D, technology costs, in the sense that the Starship won't have to be thrown away after traveling to the moon. And for Blue Origin, that's about $200 million. The key thing to take away from this is that our business model and our perceived scale of our business model, or essentially the number of ships that we are trying to refuel, is what drives the size of our technology stack. So, and I'll talk a little bit more exactly about what our technology stack is, but the liquid oxygen requirements drive the size of our processing plant, which is what is responsible for creating the liquid oxygen, which drives the size of our rovers, which is responsible for getting the raw materials. And that in turn drives the size of our power plant, which is responsible for producing electricity for both of these other subsystems. Here's a quick overview of our technology and some renderings. Our renderings aren't exactly like what all of these pieces of technology look like, but they're an accurate enough model. The 3 core components or subcomponents are the lunar mining rovers, the processing plant, and the what we're calling power towers, or essentially really tall solar panel fields. For the full-scale version, the solar panel field is actually about the size of a football field. So to give you guys a sense of scale. And we will need about 50 rovers in total for our second demo mission, or a second mission after our demo mission. So here's a deeper look into the rover itself. Here's an image of one of our testbed rovers that we made like a year ago or so. The purpose of the rovers is to be able to mine and haul about 0.5 metric ton of icy regolith. And when I mention icy regolith, I'm essentially just saying lunar dirt mixed with water. This is the precious dirt of the moon that has the water, which we will later process into liquid oxygen. The key thing about where the icy regolith is located on the moon, it is located in the PSRs, or the permanently shadowed regions of the moon. These are typically found near the moon's south pole, and they're some of the coldest and harshest environments in the solar system. Temperatures can get as cold as about 40 Kelvin, which is negative 200, I think 70 some degrees Celsius. Basically an unimaginable, level of cold. The environments are very dusty, and the terrain is quite complex. You can get slopes of, up to about 30 degrees, 40 degrees. It can be very rocky, so it's very difficult to access these, permanently shadowed regions in these cold traps. And finally, the rovers have to be able to survive a lunar night. A lunar night is 15 days of total darkness, where your rover body is essentially radiating all of its heat to the environment. Its onboard computers, its motors cannot, get infinitely cold. So somehow you have to heat your rover effectively so that it won't die during the 15-day lunar night. This drives a lot of power requirements, and why it's been so difficult to be able to survive a lunar night, and why we've kind of stayed away from the permanently shadowed regions and the, lunar South Pole. Here's a quick design overview of our rover. This model that I have here is more accurate to what our real life rover really looks like. We really tried to take on kind of a simplistic design approach. What that means is we try to reduce the number of moving parts. Anything that moves is subject to getting essentially destroyed by lunar dirt and lunar dust. Like I mentioned before, they're like tiny little knives that have not been eroded. And so they can get into your bearings, they can get into your actuators, and they can essentially ruin them and make them unusable. So anything that moves is considered a point of failure. With that, there are a total of 17 points of rotation or actuation placed throughout the entire rover. As you can see, the rover has 4 legs. Each leg is independently steered, has its own drivetrain, and has an articulating suspension leg, such that the rover can lift itself up, it can lower itself down, and it can tilt in any 4 of its legs' angles. We decided to, give each suspension leg this capability so that it can access the, the sloped and harsh terrain environment of the permanently shadowed regions. Along with its suspension legs, as we call it, are 2 what we call ice collection systems, or ICS arms, on the left and right side of the rover. The ICS arms are designed with 2 drum buckets that spin forward and collect material in themselves when in use. The buckets, it's a little hard to demonstrate. I can kind of show with my hand. They take little lateral cuts at the surface, and then they have an internal baffle structure that allows dirt to fall into them, but doesn't allow dirt to fall out of them when spinning in one direction. And then once the material has been collected, the 2 arms flip up and over the this tank that you see here on the back. We call this the regolith tank. The 2 arms articulate, flip up and over, and spin the drum buckets the opposite way to deposit material into the tank. Main reason that we chose this sort of a design for being able to mine is so that we reduce points of actuation. We're able to mine, collect, and store material with an arm that only has 2 degrees of freedom. Then finally, we have the dump bed, or what we call as the regolith tank on the back of the rover. This is sized to hold the 500 kilos that the rovers need to haul, and is able to tip backwards and over into the hopper, or the collection unit on the processing plant. And I'll talk a little bit more about the specifics of the processing plant in a bit. And again, some of the challenges that the rovers have to face: it is in a radiation environment, so its onboard computer will be subject to having its bits flipped. So either you use, some sort of a shield or a rad-hard operating system that can do a double check on your bits. This is a whole another subtopic that I can dive into. It has to handle the lunar dust, which I've talked a lot about. The large temperature fluctuations, like I mentioned, it can get as cold as 40 Kelvin and as hot as 54 degrees Celsius. As we all know, metals contract and expand. You'll have different types of metals on throughout your rover. And so making sure that that throughout their expansion and contraction, that they're still, functional. And finally, it has to handle a hard vacuum. All of its bearings, all of its motors need to be able to survive in the vacuum of the moon. Here's a quick overview of a coal trap on the South Pole. And I just want to quickly highlight Shackleton's crater here. I know this looks really tiny, but this is about the size of San Francisco, where I'm at right now. And there's large quantities of water present here. And this is the area where the rovers will, be traveling to and will be accessing. Anything that's shaded dark here is in a permanently shadowed region. Permanently shadowed regions can only exist on the moon because of the moon's orbit around the sun, as well as the tilt of its axis. Great, so let's look more into the processing plant, which is the second component that we need to engineer. Its purpose is to accept raw icy regolith from the rovers, take that icy regolith, filter the water from it, split the water into its constituents, hydrogen and oxygen, using hydrolysis, and then store the oxygen and liquefy it, which we will be later selling to large vehicle manufacturers such as SpaceX. When I talk about the processing plant, I'm going to further divide it into its two subsystems, the refinery and the hydrolyzer. So here's a quick overview of the refinery. Like I mentioned, its purpose is to accept the raw icy regolith and then sublimate the water. It is essentially just an oven that is meant to cook the icy regolith, heat it up to a temperature where the water escapes, and then we can capture it and condense the water. Once the water escapes, we run it through the condenser because the electrolysis unit needs the water to be in a liquid form rather than a gaseous form. And then after it's condensed, it is stored in the electrolysis antechamber to be split. The major challenge of the refinery is power. This is really what drives the power requirements and the sizing of the solar panel. And it also has the most potential to be the most inefficient part of the entire process. When I say inefficient, I mean power inefficient in the sense that when you heat icy regolith, a lot of the energy that you are using to do that, or to heat it to its required temperature, is going into the dry regolith itself. Typically, icy regolith is only about, in the best case, 10% water by mass, usually closer to 4%, and in the worst case, about maybe 1 to 2% water. That's a lot of energy that you're spending to heat a lot of material that you won't really be using later. So you essentially dump all of that energy out after you deposit your desiccated regolith. This is the biggest challenge of this part of the project, is finding a way to essentially selectively heat the water and the icy regolith. Oh, and one other thing I should mention there. Probably a lot of people are immediately thinking, just use microwaves. Microwaves selectively heat water. They're less good at heating ice and are not as great at heating icy regolith as well. So while microwaves are one potential solution, they come with a lot of caveats and a lot of inefficiencies as well. So people have looked into many different ways to refine the water from the icy regolith. Here's a quick overview of the hydrolyzer. We'll be using a PEM style of electrolysis, purpose being to release oxygen gas from the condensed water and then storing and liquefying the oxygen. Biggest challenges here is maintaining the temperature of the PEM electrolysis. It has a, as you can see, 20 to 100 degrees Celsius temperature range in which it must function. We have to keep this entire structure at its required temperature throughout the processing plant's entire life. This includes being able to survive the winter night. And finally, here are some of the requirements of the power tower. Like I mentioned, the scale of the power tower and the worst, not the worst case, in its largest case, or for our mission 2, is about the size of a football field. This is because the refinery and the rovers need about 1 to 10 megawatts. It's, yes, mega, not kilo, megawatts of power to function. Not only that, we have to somehow place all of these power towers inside of a rocket, which is clearly, volume limited. We can't bring an entire football field, on a rocket itself. So this is really a sort of, packaging and design problem. We're still developing the power tower right now, and I don't really have a good, prototype here to show you. But actually, if I go back here, there are 3 main pieces that we'll be using, which is a carbon fiber deployable boom, an unfolding top hinge, and then rollable solar panels that are rated to, handle a vacuum. These are the 3 main components, and the way the design works is you start off with the base down here. Your carbon fiber tube unrolls and deploys vertically. Once it's reached the top, the hinges unfurl and then drop the rollable solar panels down. This is the way that we're trying to essentially get the entire solar panel to package itself while it's on the rocket. For a sense of scale, the boom height is about 30 feet. Here's an example of an unrollable carbon fiber boom, as well as a rollable, solar panel. Like I mentioned, the biggest challenges here with the power tower is being able to package it. The power tower also will have to track the sun, and it'll essentially be spinning at a rate of about, 1 revolution every month. So that's another added degree of freedom that we have to include in this mechanism. Great, and then we'll discuss a little bit of the next steps for Starpath and for in-situ resource utilization and enabling life in space. So as Dr. Rhodes had mentioned, we competed in NASA's Break the Ice Challenge, or in the phase 2 of the Break the Ice Challenge, which involved creating a rover that is able to mine about 12 metric tons of concrete over a period of 15 days. The next phase of the competition is taking this same rover, demonstrating it at NASA's facility against other, lunar rovers produced by, other small businesses or other large companies, and also demonstrating that your lunar rover is able to mine in low gravity scenarios. Mining on the moon is very different than mining on Earth because a lot of machines here on Earth kind of use their own weight as a counterbalance to the digging force. Essentially, when you stick a shovel in the ground, you don't go flying off into space because of your own weight. However, on the moon, you don't have that luxury because you're at 1/6 G, and, we all saw the cost per kilogram. Every kilogram that you add is going to add another $100. So say if you want to add, if you require a metric ton of material to not fly off into space, well, that's a huge overhead. So during this next phase of the competition, we'll be demonstrating our low gravity mining abilities and ability to traverse complex terrains at NASA's facility. One of the rewards of this competition is being able to test our rover in a dusty thermal vacuum chamber. This is essentially a way to create the environment that the rover will have to experience. We really want to use that to demonstrate to the world that we are the state of the art when it comes to, lunar mining rovers. So this is the next step for our company and for the rover program in general. In parallel, we are still developing our power tower and our processing plant. Finally, the next steps for enabling life in space for NASA are the Artemis missions. Artemis plans to send to have crewed missions. They plan to send their own rovers, which will travel into the permanently shadowed regions, just as the Japanese did, just as Chandrayaan-3 did. Specifically, they have this rover called Viper, which is meant to sort of map the cold regions or the cold trap regions of the moon, which we will then use as data for our rovers. So these next upcoming missions for Artemis are critical for enabling life in space because of their ISRU demonstrations and their desire to return astronauts to the surface of the moon. And finally, I just want to highlight one big NASA contract, which is called Lift 1. Lift 1 is a $250 million NASA contract that is specifically for in-situ resource utilization. The definition of this contract is to have technology that can fly to the surface of the moon and demonstrate the ability to use the resources there to produce rocket propellant, either from icy regolith or from desiccated or dry regolith not found in the permanently shadowed regions. For Lift 1, we are looking to partner with big vehicle manufacturers and apply to this contract for the next stage of our company. And with that, that's all I have for this presentation. So thank you very much for taking the time to listen to me and about in-situ resource utilization.
Yeah, thanks. And thanks, Mihir. And guys, if you have any questions, drop it in the chat. Well, I've been writing furiously, Mihir, so I have a lot of questions. You answered by one about how do you simulate, how do you test your design and how do you simulate that environment? But I had a question about how do you address things like waste management, right? If your yield from a half a ton, like if the max is 10%, you're gonna have all this waste. Is the idea then to just sort of drop it? Like, I mean, is it basically, yeah.
Yeah, great question. So actually, let me go into my slides here. See if I can. So this being kind of a mock-up of our processing plant, this chamber here is meant to represent the chamber that drops the desiccated dry regolith into another rover, which will then carry that waste and deposit it somewhere else on the moon. So that is one way that we're thinking of managing the dry regolith. Another option that started popping up for us is a lot of other companies are interested in raw regolith as an input into their own business. Companies such as Astroforge are looking to take dry regolith and essentially make building blocks or bricks out of it to support construction on the lunar surface. Other companies are looking to perform what is known as molten oxide electrolysis, which is the process of taking dry regolith and essentially doing what hydrolysis is for water, which is just using an electric current to split your atoms apart on the dry regolith, which is typically silicon oxides, and then producing silicon and oxygen. We just don't do that because that's really power intense, and we believe that targeting the water is a better route to go. But other companies have this as kind of their business model, and so on. Companies such as Blue Origin, who can kind of eat the overhead costs of not being able to power a molten oxide electrolysis reactor immediately. So those are some other options for the waste material that we'll be producing. And that's this here is the chamber that produces it. So yeah, I
Nice.
hope that answers your question.
Yeah. Terry in the chat wants to know, what amount of setup is there for a technology stack? Is there a lot that needs to be done manually? Like, do you expect astronauts to be doing your, sort of construction for you, or how once landed, how long do you expect setup to take prior to going into production?
Yeah, great question. We trying to see how much I can share here. We will not be using humans to do any of the setup. They will be robotically set up themselves. Specifically for, I guess, like the rovers will essentially be coming in a in a box, which can handle the vibrations of a rocket, and we'll then kind of just drive out of the box once the box is placed in the location that we want to be set up in. That location being a region which is very close to the South Pole. I can't exactly describe how we're going to get that box to the South Pole because I'm under NDA and export control laws. But yeah, once we're set up there, the rovers will be able to drive themselves out. The processing plant will be carried and placed robotically, and we'll essentially just have to statically remain in one spot. So there's not much, setup tasks required there. It just needs to be carried out of its container.
Right. Nice. Then that's the one unboxing video that would be very, very fun to watch.
Yeah.
Right. But you brought up this idea of what kind of how you would get to the moon, how you would get to where you're going to set up. But there are like you brought up export control. It seems like so that brings up the question that Dina has asked, which is, how do Starpath and other companies handle questions about who has the right to access the moon? How do you keep the moon free from pollution? Because, I mean, it's not a lot of atmosphere, but there is some there. And then now there was a controversy recently about the idea of the moon being a sacred place, and these controversial moon questions that, that may sort of thwart you. So what's the cislunar economy think about that, or how are you addressing that?
Yeah. Great question. I think in general, the attitude towards that has been, okay, well, producing water and producing hydrogen and oxygen is actually making the moon habitable. And so we're not per se, like mining on Earth is kind of associated with pollution and, degradation of the environment. It's kind of the opposite case for the moon. We're making the moon, habitable. So, I guess that's kind of the attitude that cislunar, companies have towards that. The other thing is there is a ton of water on the moon. You could have, like, it would take our lifetime and several companies of moon mining rovers to actually use up all of the resources and water there. Not just our lifetime, several lifetimes. So right now it's just kind of an attitude.
It's not a political question. It's not okay. But I mean, I just heard recently of a whole branch of something called space law. So I'm sure we'll get space lawyers.
Exactly. Yeah. So things still get, sticky from there, even if there are, even if there is a lot of water that is accessible. So yeah, that things change day to day there. Laws change day to day. So pretty much the idea is we just have to keep up with it and make sure that we, we're not breaking any laws or
don't do that. Don't. I need no lunar laws or space laws or so. My question to you is about things like what are the challenges because you're a startup company, this is a business venture. Obviously, you have the goal is to make money, is to make this profitable. So what are the challenges when you go in front of venture capitalists? Like what are some of the issues that you have to sort of soothe them on?
Yeah, so specifically for venture capitalists, you can kind of look at our company in two ways. One, it's a business risk. The second is it's a technology risk. So on the business risk front, we have to really convince them that there will be a cislunar economy, and that just operating in Leo and so on Leo, I mean low Earth orbit, is not the only place where space startups can exist. Space startups such as like Varda, which does satellite or space manufacturing. They essentially manufacture like medicines in space or in microgravity. So convincing them that there will actually be an economy surrounding the moon is one step. The second step is explaining to them that we can actually pull off this, creating all of this technology. We're still pretty young, new grads. We're not like engineers with decades of experience that are previous like leads or chief engineers or whatever at other aerospace companies. So
just experience.
Proving our mettle is another big challenge when we pitch to venture capitalists. And then finally getting them to understand everything is another challenge in and of itself, and what's unique about us as opposed to other companies which do kind of similar things. So
well, and that brings me to the fact that you said you weren't, this is 3 of you when you started, you're up to 6 right now, so like you've doubled. But how much of this has been you learning and then going so out of your mechanical engineering comfort zone? Because you've probably had to be electrical, computer, product design, you've had to do a lot of that. Like how have you been able to keep up with that?
Man, it's been really difficult. It's just a lot of late nights, 6-day weeks, over 12 hours each day. Just teach yourself from first principles how to do the engineering, if it's technical work you need to do. So for example, right now I'm working on the design of the battery for rover, the bus work that needs to be done on the battery, as well as all of our hermetically sealed like wire harness pass-throughs. So from there, I've had to just, I don't know, I guess teach myself a lot of electrical engineering and such.
Chemical engineering as well, right? Like a lot of the battery, yeah.
Exactly.
And actually, that sort of brings me to my next question, which is what kind of developments in material science are you kind of excited about in terms of how they will help you, get that the battery life to stay longer and things like that? Like what are some of the things that material properties that you're sort of looking for in the next bunch of materials?
Yeah, so specifically in the field of material science, we're really looking forward to seeing developments in compliant materials. For example, like silicone, for a PTFE is another example. Compliant materials are, the majority of the body of the rover and such is all, metallic. It's 6061 T6. The wheels, however, which are compliant, they're not just fully metallic structures. Those need to use such materials like I just mentioned, silicone and PTFE, and not outgas, and be able to touch extremely cold temperatures, and not reach their glass transition point. So any sort of developments in compliant space grade materials is vastly useful to us.
Yeah. And there's one more question about how much of the operation is going to be run from the surface of the moon itself. So how much will require hands-on, and how much of the operation would you be doing remotely from Earth? And then do you have to worry about that kind of, send a message, wait for it to, like what's that lag look like?
Yeah, so ideally the rovers would be fully autonomous. They'll likely be semi-autonomous. The portion where the rovers are operating outside of the permanently shadowed region, specifically the setup task for navigating and placing the processing plant as well as the power tower, it's going to likely be done from Earth. After that, the rover will essentially to do mapping on the moon, since V-slams, or I don't know if people are familiar with visual slams and computer vision. You can't really use that on the moon like we do on Earth for self-driving cars. And so from there, it has to set up essentially waypoints for itself to, for it to be able to navigate itself. You can't communicate to technology that is in a permanently shadowed region of the moon. So while the rover is doing its mining operations and such, it'll have to be autonomous. One other method of tracking or localization and mapping that we've thought of is star tracking, where you essentially look at the constellations that are above, However, that's not very accurate. I believe you can only map yourself up to like 10 square meters or something, so it's not great, but yeah.
It is old technology, right? So the oldest. So thank you very much. Are there any more questions for Mihir? Otherwise, guys, this was the last talk. Thank you, Mihir, for being a really wonderful end to our 8th Roger That academic conference. We invite you to come to Seedman today and participate in the rest of the activities, and then at the museum tomorrow, where we will wrap up. Dina's put the surveys in the chat. Please don't forget to do the surveys. I want to thank you all for coming out to Roger That again, and thanks, Mihir. Thanks for your time. This was wonderful.
Of course, let's get to the moon.
Yes. Bye, guys. Mark your calendars for the next Roger That.
When is the next one?
Oh, next year.
So always the end of February, because
always the middle, start to the middle near Roger Chaffee's birthday. That's what we try to have it. But this is our 8th.
I attended before and I love it, but this year I didn't get a reminder until like 3 days ago, and I was like,
oh no, yeah, no, we'll do a better job. We all have day jobs doing other things, and so it gets nuts.
I just love it so much. Thank you.
Thank you so much, Catherine. We appreciate this very much. Yeah. Don't forget the series. Bye-bye. Yep. Bye.